right, everyone, get ready because today we're going deep into AI efficiency.
Ooh, exciting.
Yeah, we're talking about those huge large language models.
LLMs.
LLMs, right? The ones that seem to be like everywhere these days.
Taking over the world, right?
Exactly. But have you ever thought about how much computing power it takes to even run those things?
Yeah, it's a good question.
It's a lot.
And a lot of researchers are really trying to figure that out.
Yeah.
It's a big problem actually, because even with all the new hardware
Yeah.
training and running these massive models, it can be really expensive,
Well, yeah.
and it uses a ton of energy.
For sure. That's why I think today's deep dive is so interesting.
Okay.
We're looking at this paper.
Yeah.
It's called QuEST Stable Training of LLMs with 1-bit weights and activations.
Catchy title.
I know, right?
I know.
It's a mouthful. But what they're proposing in this paper could be a total game changer.
Okay, I'm intrigued. What is it?
So what's really cool about it is that it challenges this idea that we have in AI. You know, that idea that higher precision equals better accuracy.
Right, more bits is better.
Right, exactly.
More is always better.
For the longest time, we've been working with models that use 16-bit precision for their calculation.
16-bit, yeah.
But this QuEST thing, it suggests that we might be able to do it with a lot less.
Oh, interesting.
So we could basically shrink these models without making them dumber.
Okay, yeah, so how would that even work?
Right.
What would that look like?
So basically, they introduced this method called quantization-aware training,
Okay.
or QAI.
QA, got it.
Unlike that, what is it, PTQ?
Post-training quantization.
Yeah.
Right, which is where you kind of
Yeah, where you try to
you try to shrink it.
Yeah, shrink it after you've already trained it.
Right, exactly.
QAI does it during the training process.
Oh, so the model's learning with that lower precision already built in.
Yeah, exactly. So it can adapt to it, from the beginning.
That's really clever.
And potentially, it leads to better accuracy.
Even though you're using way fewer bits.
Even with drastically reduced bit widths, yeah.
Huh, that's amazing.
So instead of I don't know, trying to squeeze an elephant into a tiny car,
okay, yeah.
we're training a smaller, more agile animal,
Right, from the get-go.
From the start.
Yeah, that makes sense.
But how do you even train a model with that low of a precision?
Yeah, that's the question.
This paper, it talks about using weights and activations in just 4 bits.
4 bits? Wow.
Or less.
That seems almost impossible.
I know.
How does that even work?
Yeah, so that's where the real cleverness comes in.
Okay.
They use all these techniques to make this compression possible.
Okay.
One of them is called the Hadamard transform.
Oh, I've heard of that. It's like a mathematical tool, right?
It is.
To help normalize the distribution of weights and activations.
Yeah, I'll admit, the actual math is a little over my head.
Sure, yeah, it can be complicated.
But can you break it down a little?
Yeah, sure.
What does normalizing actually do in this context?
Okay, so imagine you have a data set with values that are all over the place, right? Some are really big, some are really small.
Okay, yeah.
It's really hard to represent that data accurately if you only have a few bits to work with.
Right.
The Hadamard transform, it kind of redistributes those values.
Okay.
It brings them closer together so they can be represented more effectively, even with lower precision.
Oh, so it's making the data
more compact. Right.
But without losing the important information.
Yeah, exactly.
That's really cool.
Yeah, it's a neat trick.
But what about the actual learning process?
Right.
How does the model adjust to these lower precision calculations?
Right, so that's where another really clever part of QuEST comes in. They call it the trust gradient estimator.
What?
The trust gradient estimator.
Okay, another mouthful.
I know, right?
So what is that?
But basically, it's a mechanism that helps the model learn effectively.
Okay.
Even when there are those quantization errors,
Hold on, quantization errors. What are those?
Oh, right, yeah.
Why do they matter?
So remember how we're representing the weights and activations with a limited number of bits?
Yeah.
Well, that means we're kind of losing some information, right?
Okay.
And that loss of information, it can introduce errors into the calculations.
And that messes things up.
Yeah, it can affect the model's learning process.
So the trust gradient estimator helps with that.
Yeah, it
How does it work?
basically it acts like a filter. So during training, the model is calculating gradients.
Gradients?
Yeah, those are they indicate how the weights and activations should be adjusted to improve accuracy, right?
Right.
But with quantization, some of those gradients might be misleading.
Because of the errors.
Because of the errors. Exactly.
Right.
So the trust gradient estimator kind of like identifies those potentially unreliable gradients,
Okay.
and it downplays their importance. So the model focuses on the more trustworthy ones.
Oh, so it's like a quality control system.
Yeah, exactly. That's a good way to put it.
It makes sure the model's not, like, led astray by these errors. It's
Exactly.
amazing how they, like, thought of all
It's
this.
really clever.
But I'm curious, like, does it actually work?
That's the million-dollar question, right?
Yeah.
So to test it out, they trained a bunch of these llama family model
Uh-huh.
using QuEST with different levels of precision, like all the way down to 1 bit.
Wait, 1 bit?
1 bit.
You mean like just ones and zeros?
Just ones and zeros.
Did that even work?
Surprisingly, yeah. I mean, it wasn't as accurate as the higher precision models, but it did show that QuEST could, like, achieve some level of performance, even with that extreme compression.
Wow, that's kind of mind-blowing.
I know, right?
But I imagine there's like a sweet spot, right?
Yeah, you're right.
Somewhere between 1 bit and the standard 16 bits.
Exactly. And that's one of the coolest findings of this research.
Okay, what is it?
They discovered that in many cases, 4-bit precision is like the optimal point
Okay.
on the Pareto-optimal frontier.
Wait, hold on.
Pareto-optimal frontier, I know, it's a mouthful.
What is that?
So it's basically a way of like visualizing the trade-off between accuracy and model size.
Okay.
The Pareto-optimal frontier represents all the solutions where you can't improve one without sacrificing the other.
Right.
And in this case, they found that 4-bit precision often offered the best balance.
So we could be talking about shrinking these huge models by like a factor of 4
Potentially, yeah.
without losing a ton of accuracy.
Exactly.
That's huge.
It is.
And remember when we talked about the overtraining regime earlier?
Yeah, where you train with more data than you need.
Yeah, well, even in those cases, 4-bit precision was still good.
It held its own.
So even when we're pushing these models to their limits, this lower precision still works really well.
It's pretty impressive.
That's amazing.
And what makes it even more significant is that this 4-bit sweet spot, it might not just be about convenience.
What do you mean?
Well, the researchers, they think it could be the most efficient choice, even if we had unlimited computing power.
So even if we had all the computers in the world, 4-bit precision might still be the best way to go.
That's what the research suggests.
That goes against everything we thought we knew about AI training.
I know, it's pretty wild.
It's really interesting for our listeners who might be thinking, why should I care about this?
Right.
What does this mean for, for them?
Okay, so imagine a world where AI models are not just super powerful, but also super accessible.
Accessible, what does that mean?
Well, think about it.
Okay.
Smaller, more efficient models, they don't need, like, crazy powerful hardware to run.
Okay.
So you could potentially run them on, like, a wider range of devices.
Oh, okay.
From smartphones to even like little tiny embedded systems.
So instead of needing these huge data centers,
yeah,
we could have AI running like locally.
Exactly. On your phone, on your watch, who knows?
That's incredible.
It could really democratize access to AI, make it available to like smaller companies, researchers who don't have a ton of money.
Yeah.
And even just like regular people.
What about energy consumption?
Oh, right.
We all know that training these models, it uses a ton of energy.
It does.
Would QuEST help with that?
Yeah, absolutely, because it reduces the computational demands.
Oh, okay.
So it could, like, significantly reduce the energy footprint of AI.
Make it more sustainable.
More sustainable, more environmentally friendly. Yeah.
That's amazing. This is, like, groundbreaking stuff.
It really is. We might be seeing a major shift in how we think about AI.
Totally.
And what's even more exciting is that QuEST's potential goes beyond just shrinking models.
What do you mean?
It raises this like really interesting question. Can we generalize these findings to other types of AI models and applications?
So this could be just the beginning.
It very well could be.
That's wild. Imagine if we could apply these same principles to, like, AI models used in robots or medicine or even, like, scientific research.
The possibilities are endless.
And that leads us to the next part of our deep dive.
Okay.
We've talked about the basics of QuEST and, like, how it could change things.
Yeah.
But now I want to know, how does this actually work in the real world?
Let's get into it.
Yeah, let's dive into the detail.
Yeah.
So we know that QuEST could really change things up.
Yeah, big time.
But how does it actually work on, real-world hardware?
That's a great question. And the researchers, they really wanted to make sure that QuEST wasn't just like a theory.
Right.
They wanted to make sure it could be implemented and run efficiently on the hardware we have now.
So they didn't just, like, stick with simulations.
No, they went a step further.
What did they do?
They actually developed custom GPU kernels,
GPU kernels. Okay.
which are basically like specialized programs optimized for running QuEST models
Okay.
on NVIDIA GPUs.
Right.
Specifically, they tested it on the NVIDIA RTX 4090.
That's a pretty powerful graphics card.
Oh yeah, a lot of people use it for AI stuff.
So what happened? Did they see, like, good results?
Yeah, the results were really impressive.
What did they find?
The QuEST models, they ran way faster on the RTX 4090
Oh, really?
compared to the standard models with higher precision.
So how much faster?
It depended on the model size and the type of layer being processed, but the speedups ranged from like 1.2x to 3.9x per layer.
Wow, that's a pretty big improvement.
It is.
But what about, like, the overall performance? Did those speedups translate into, faster training times?
Yeah, definitely
But
much faster. For the whole process, they saw speedups of 1.3x to 1.5x.
So the entire process of training a model was that much faster with quEST?
Yep, pretty cool, huh?
So not only are the models smaller, but they're also faster to train.
Exactly.
That's huge for anyone working with AI, especially people who don't have access to, like, a ton of computing power.
Right. It makes AI more accessible to, researchers, startups, even individual developers.
That brings up something else from the paper about different data formats.
Okay.
They mentioned a new FP4 format that works with NVIDIA's Blackwell architecture.
Right, right.
What is that?
So different hardware platforms, they support different data formats.
Okay.
And FP4 is this, it's a pretty new format that offers 4-bit floating point precision.
Okay.
It's designed for NVIDIA's Blackwell architecture.
Which is going to be like the next big thing in AI hardware.
Most likely, yeah.
So it's like a special language just for this new hardware.
Exactly. It's optimized for communicating with that specific architecture.
That's cool. And did quEST work with this FP4 format?
Yeah, it worked really well, actually.
How did it compare to other formats?
So they looked at INT, which is integer, and FP, which is floating point,
Okay.
and even INT plus sparse formats.
And what do they find?
4-bit INT consistently performed the best
Okay.
in terms of effective parameter count.
Okay, hold on. What's effective parameter count?
So it's basically a way to measure how many parameters are actually contributing to the model's performance.
Oh, interesting.
Not all parameters are equally important, you know?
Okay.
Some have a bigger impact on the model's output than others.
Got it.
And by using a lower precision format like 4-bit INT,
Yeah.
you can often reduce the number of parameters.
Without messing things up.
Exactly, without sacrificing the overall effectiveness of the model.
So you're basically getting rid of the parameters that aren't really doing anything.
Yeah, it's like trimming the fat, you know?
Yeah, I got
But
it.
what's amazing is that quEST, combined with this 4-bit INT format,
Yeah.
it's really good at doing that.
It's crazy to think that you can actually get better accuracy with lower precision.
I know, it seems counterintuitive, right?
Really?
But it just shows that we're still, like, learning about how precision, accuracy, and model efficiency all work together.
That's what makes this research so important. It's challenging our assumptions.
Yeah, it's pushing the boundaries.
And it's not just about optimizing for one thing, like accuracy or model size.
Right.
It's about finding a balance between a bunch of different factors.
Exactly. Speed, efficiency, even environmental impact.
As AI becomes more and more common,
Yeah.
we need to think about how much energy it uses.
Right. Sustainability is really important.
And quEST could be a way to make AI more sustainable.
Absolutely. It could help us achieve amazing performance without using a ton of energy.
That's really cool. The paper also mentioned combining quEST with sparsity techniques.
Oh, yes, sparsity.
Can you talk about that a bit?
Sure. So sparsity is this idea that a lot of AI models have a lot of redundancy.
Redundancy.
Yeah, like not all the connections between neurons are equally important.
Okay.
Some connections are really important for the model's output,
Uh-huh.
but others, they don't really matter that much.
So it's like,
It's like a network of roads, and some roads are super busy highways,
yeah,
while others are just like little back roads that no one uses.
I like that analogy.
So sparsity techniques, they aim to like identify those less important connections
Okay.
and then prune them away.
Like get rid of them.
Yeah, essentially it makes the model more streamlined and more efficient.
So the researchers think combining quEST with sparsity could make the models even smaller.
Exactly. You could get some crazy compression.
That's amazing. Models that are just as powerful, but like super tiny and efficient.
Yeah, it's pretty wild to think about.
What would that mean for like AI applications?
Oh man, the possibilities are endless.
Like what?
Imagine running complex AI models on tiny devices, things with very little processing power.
Right.
Think about robotics, wearable technology, maybe even like implantable medical devices.
So like the whole field of AI is about to get a major upgrade.
In terms of efficiency and portability, yeah, I think so.
This all comes back to like rethinking how we design and train AI models.
Right, it's a fundamental shift.
This is a perfect time to move to the final part of our deep dive.
Okay.
We've talked about the technical stuff,
Yeah.
the benefits of quest, its impact on hardware and data formats.
Right.
Now I want to talk about the bigger picture.
The big picture, yeah.
What does all of this mean for the future of AI?
Let's get philosophical.
This is really cool, like just one research paper and all these new ideas.
I know, right? It's pretty wild.
It really does feel like a paradigm shift in AI.
It's definitely a big moment, and like any breakthrough, it leads to even more questions.
I guess that's what makes it so exciting. So what kind of questions are we talking about?
Well, one of the big ones is, can we apply what we've learned to other types of AI models?
Oh, that's interesting.
Right now, quest has mainly been used with LLMs,
Right.
but could it also work with other architectures?
Like what?
Like convolutional neural networks,
Okay.
the ones used for image recognition,
Right.
or recurrent neural networks
Fair.
for time series analysis.
And if it does work for other models, I mean, that would be huge, right?
Oh, yeah, it would change a lot of things.
Like what?
Well, think about robotics.
Okay.
Those models need to run on devices that don't have a lot of power.
Right. They need to be efficient.
Exactly. Or in medicine, smaller, faster models could, like, analyze patient data in real time.
Wow, that would be incredible.
It would.
But with all this talk about efficiency and new possibilities, what about the ethical side of things?
That's a really important point.
I mean, if AI becomes even more powerful and easier to access,
Yeah.
do we need to rethink how we develop and use it responsibly?
Absolutely. Efficiency is important, but we can't forget about ethics.
Right.
We need to make sure these advancements are used for good.
For the benefit of everyone.
Exactly. As we move forward, it's super important to have conversations about the impact of these technologies.
Yeah, I agree.
And we need to develop guidelines and regulations to promote responsible AI development.
It's like a reminder that just because we can do something doesn't mean we should.
Right. We need to think about the consequences.
We need to make sure we're using AI for good.
Exactly.
So where do we go from here? What's next for quest and these new ideas about AI efficiency?
Well, the next step is to keep testing quest,
Okay,
Try it out with different models and different applications.
makes sense.
We need to see how well it works beyond LLMs.
Right.
And explore what it can do in other areas,
And what about combining quest with other techniques?
like sparsity.
Yeah, sparsity.
That's definitely something to explore.
It could lead to even more compression
The models could become way smaller.
and even more efficient.
Exactly.
It feels like we're just at the beginning of something really big.
I think so too. It's a very exciting time for AI research.
We're at a turning point.
And the choices we make now will have a big impact on the future of this technology,
It's not just about bigger and more complex models anymore.
right?
It's about finding smart, efficient solutions.
That make AI better for everyone.
More accessible, more sustainable.
Exactly.
Well, on that note, I think it's time to wrap up our deep dive into quest and the future of AI.
Sounds good.
We've talked about a lot today,
We have.
from the technical details to like the big picture stuff.
The philosophical stuff.
And I hope everyone listening has found this as interesting as we have.
It's been a great discussion.
It has. And remember, the world of AI is constantly changing.
Always evolving.
New discoveries are happening all the time.
Every day.
So stay curious.
Keep learning.
And who knows what amazing things we'll find next.
The possibilities are endless.
Until then, keep diving deep.